I'm so sorry that I can't be there today, and I appreciate your understanding and patience. I'm going to walk through our study called Exploring Social Contagion in a CSCL Environment with a Social Robot. My name is Nikki Lobczowski. I'm an assistant professor at McGill University, and this work comes from my postdoc at the University of Pittsburgh, and I'll just take a second to acknowledge my amazing collaborators there. One of the main benefits of collaborative learning is that it allows students to integrate diverse perspectives and then converge with their peers, which can impact behaviors, perceptions, and emotions. This aligns with Manstead and Fisher's idea of social appraisals, or those of social events that often incorporate others' reactions, which can lead to experiencing emotions that would be potentially different in alternative settings. But the idea of social contagion incorporates interactions more broadly, focusing on the mimicry of both behaviors and interactions. And so, importantly, individual differences can impact behaviors and interactions, resulting in many potential interactions and possible contagion. Little is known about social contagion in learning environments, and even less with human-computer interactions, such as seen here when two students work together with a social agent. Agent and robots that align to individual students in a variety of capacities, such as lexical and emotion, have produced positive outcomes during a collaboration. And so a term that's very much used in this field is entrainment, to deal with that kind of lexical and emotional contagion. But even less is known about how macro-level processes related to social contagion might operate or function in these settings. This project involves a now robot named Emma. Emma is a teachable robot who helps students learn math by having them explain how to solve complex ratio problems to her. This image shows how Emma processes spoken messages from students through automatic speech recognition and feature extraction. She processes what students are saying in real time, detects keywords and phrases, and then provides a response from an extensive database of utterance. So our main goal for this project is to explore how social contagion emerged in a human-human robot learning environment. In this particular environment, the students talk with each other and Emma. This study was part of a larger experiment that also included solo learning. Here we focus only on dyadic data. Participants completed a pre-survey on motivational constructs and attitudes about collaboration in robots, Likert type items, an assessment, 8 ratio problems independently, engaged in the collaborative activity via Zoom, and then independently completed a corresponding post-survey and assessment. Students also often solved a problem and talked about it with their partner, then explained a procedure to Emma in natural language, who processed the response and provided an explanation in real time. So for this study, we decided to do a representative case study in order to illuminate the differences between distinctive groups of students. So we used students' pre-survey ratings of attitudes about collaboration with questions such as, when I work in groups, I do better quality work. We calculated the average and standard deviation for each dyad. And so a high standard deviation means that they rated their collaboration preferences more similarly. A low standard deviation means that they rated them more dissimilarly. A high average means that they rated them higher or more positively. And then a low average means the dyad rated them lower or more negatively. So we selected 4 groups to show differences in these constructs. High average and high standard deviation, or positive and dissimilar. High average and low standard deviation, positive and similar. Low average, high standard deviation, negative and dissimilar. And then low average and low standard deviation, which means they rated their views of collaboration were both negative and then similar to each other. So in order to detect social contagion, we first started by coding for socioemotional interactions. So we coded for valence, positive and negative. We voted for different types of socioemotional interactions, such as turn-taking, sharing feelings, disrespect. We also coded for initiator, so student A, student B, or even sometimes Emma, which was unintentional. And then the recipient, so who's on the receiving end of the socioemotional interaction. So again, student A, student B, or Emma, the robot. For iterating, we had 2 independent coders code the first 8 transcripts until We reached an iterator reliability over 80%, and then the average across these transcripts was 76%, and then one coder coded the rest, and then with the second auditing, and then of course all disagreements were reconciled. But then we also used a text mining to measure the sentiment of the students' utterances. So for this, we used an AFIN library in R, which assigned weighted negative and positive values from -5 to 5 to each student utterance or word, calculating totals for each student in the cases. So we have a couple of examples for those less familiar with this method. So this is from our third dyad where speaker A says, correct, very cool, which was a socioemotional interaction because it was complimenting and it was directed at Emma. And then the sentiment analysis picked up on the word cool and gave it a positive 1 point. And then here's a passage from our second dyad where A and B go back and forth, and they're talking about Emma and the robots. And so that most of these, they're using the code of sharing feelings, but which is seen as a positive socioemotional code, which we'll discuss later. But the way they were talking about her was very negative in that they called her weird or an idiot or awful. And so each of those got a weighted score. So the more negative the word is, the stronger the valence is on the sentiment. But you also see things in here like sentences, which also gets a negative word. So it's not perfect, which is why we combine the two types of coding. So this coding plus sentiment analysis gives us a more comprehensive picture of socioemotional exchanges and helps us detect patterns in socioemotional interactions in hopes of detecting and understanding social contagion. So for our qualitative exploratory analysis, we considered patterns of socioemotional interactions and sentiments, integrating information about pre-existing factors to add context to our findings. So for the results, we found that all students initiated more positive than negative socioemotional interactions and sentiment, but there were differences between the groups. So dyad 1, which was our high average, so positive, and then low standard deviation, so similar, we noticed that they had good collaboration both within and between problems in taking turns. And so here are some data at the student level. So you can see 1A, both of them initiated positive socioemotional interactions, but they did not initiate any negative. There was positive sentiment across all of the turns. And you can see that they rated their collaboration very high. This is out of a possible 5 points. Dyad 2 was low average and low standard deviation, so more negative but more similar. And so they had a lot of, as we saw in the last one, many sharing feelings, but they were sharing negative feelings. So we saw a lot more negative sentiment, even though we did see a lot of socioemotional interactions initiated. Dyad 3, which is our low average, high standard deviation, we saw the student with the lower rating initiating more positive interaction, but the dyads had very few positive interactions compared to the other groups. And then finally, in our high average, high standard deviation, so positive and dissimilar, again, we saw one student we saw more differences in these students and more initiation with one student over the other. So next we'll discuss the results and comparisons between the positive and negative dissimilar groups. So just a reminder, dissimilar means there was a high standard deviation on our measure and that the positive group had a higher average and the negative had a lower average. And just for some context, in dyad 4, 4A was rated at higher than 4B, and dyad 3, 3B was higher than 3A. So we saw a lot of stuff around turn taking for both of these groups, which is a positive socioemotional interaction. And it's connected to norm setting, mostly at the beginning of the activity. And so high average group in turn 2, so at the very beginning, 4A says, so that means so it'll be my turn, so how do you want to split this up? Which was really interesting because they were the only group that negotiated this up front. But the turn taking was mostly led by 4A, saying like, it's your turn, or go ahead, or it's my turn, until turn 109, 4B says you can go ahead, it's your turn, and then they continue to alternate back and forth. But in the low average group, at turn 2, 3A says more like, does it matter which one of us talks? Do you want to talk? So there was less negotiation, less kind of contagion in that, and then just an overall lower quality of turn taking. And then turn 3, you can take this one, I'll take the next one. In the similar groups, and again, similar means low standard deviation. Again, some rated them high, so both students were a fan of collaboration, and then in the negative one, both were not a fan of collaboration. We saw a lot of sharing feelings, which is, again, a positive socioemotional interaction. In the high group, we saw them kind of talking about math, of where 1B says, so I'm not good with fractions, I might need a little help, what would you do? And then in turn 64, 1A switches and just, this one is different, so they acknowledge that. They acknowledge what they're feeling and then help them out. Whereas in the low average group, there was more of this idea of complaining or commiserating, where 2A complained about the robots in general, and Emma specifically, then 2B agreed and continued by 2A, and then later again by 2A, which we saw in the previous example. Negative comments about math initiated by 2B and then confirmed by 2A. So there was a lot of, again, sharing feelings, but it was less empathetic and more complaining or commiserating. Again, there's still positive interactions among these members, and then the AFIN was higher than other groups as well. But interestingly, we took a look at some of their other survey items, and we saw that 2A rated their interest in math, efficacy in math, and attitudes about robots most negatively overall. So there's some contagion in here, not necessarily related to collaboration, which we wouldn't expect because the groups are already similar, but we see more on interest and more on efficacy, and their NARS is negative attitudes about robots. And so we see the differences in those being some contagion as well. And so they're just overall comparing similar versus dissimilar, again, high standard deviation versus low standard deviation, we saw higher social contagion in dissimilar groups with regards to collaboration and socioemotional interactions, taking turns, which we discussed. We also saw we talk, so when they say we need to do this instead of I need to do this or you need to do this. And again, this aligns with the measure that we use to distinguish our groups. And again, we saw some contagion in similar groups, but around other constructs such as feelings about math and robots. And it suggests the need to consider other pre-existing factors when we're looking at social contagion. And again, valence matters. So the more positive collaboration ratings, the higher averages seem to be connected to higher quality interactions. And even with sharing feelings, it seemed like there was this difference between empathy and just commiserating. So quickly, we'll go over the discussion. The dissimilar groups seem to engage in more social contagion. The quality of the social contagion seemed connected to the group's ratings about collaboration. Again, the three main findings that align with and extend theories of social praises is about sharing feelings being positive exchanges, but if the negative feelings are the ones being shared, it can shift the tone of the group. Other pre-existing factors such as interest and affect for robots can influence social exchanges. And then the implementation of norms such as talk-taking kind of set the stage for later behaviors during the task. The implications for research is, again, continued exploration, measurements, and testing of social contagion. And for practice, group formation and interventions for maladaptive interactions when students are rating things high and low and similar and dissimilar. I just want to thank you again to the organizers of this symposium and for your patience. I wish I could be there. I also want to thank our funding agencies. If you have any questions, please feel free to email me. Thank you.